Ununseptium is a superheavy artificial chemical element with an atomic number of 117 and a temporary symbol of US. Also known as eka-astatine or element 117, it is the second heaviest known element and second to last element of the seventh period of the periodic table. As of 2015, 15 ununseptium atoms have been observed, 6 when it was first synthesized in 2010, 7 in 2012, and 2 in 2014. The discovery of ununseptium was announced in Dubna, Russia, by a Russian-Euro-American collaboration in 2010, which makes it the most recently discovered element as of 2015. One of its daughter isotopes was created directly in 2011, partially confirming the results of the experiment. The experiment itself was repeated successfully by the same collaboration in 2012 and by a joint Germany-Euro-American team in 2014. The Joint Working Party of the International Union of Pure and Applied Chemistry and the International Union of Pure and Applied Physics, which is in charge of examining claims of discovery of superheavy elements, has made no comment on whether the element can be recognized as discovered. Once it is recognized, the discoverers will be invited to give the element an official name. Ununseptium is a temporary systematic element name that is intended to be used until a permanent one is assigned. The working name element 117 is commonly used by researchers and in the literature. Ununseptium may be located in the island of stability, a concept that explains why some superheavy elements are more stable compared to an overall trend of decreasing stability for elements beyond lead on the periodic table. The synthesized ununseptium atoms have lasted tens and hundreds of microseconds. In the periodic table, ununseptium is expected to be a member of group 17, all other members of which are halogens. Some of its properties are likely to be significantly different from those of the halogens due to relativistic effects. Unlike the halogens, ununseptium is likely to neither commonly form anions nor achieve high oxidation states. A few key properties, such as its melting and boiling points and its first ionization energy, are nevertheless expected to follow the periodic trends of the halogens. History Prediscovery In 2004, the Joint Institute for Nuclear Research team in Dubna, Moscow Oblast, Russia, proposed a joint experiment with the Oak Ridge National Laboratory in Oak Ridge, Tennessee, United States, to synthesize element 117 so-called for the 117 protons in its nucleus. Their proposal involved fusing a berkelium target and a calcium beam, conducted via bombardment of the berkelium target with calcium nuclei. The American team the world's only producer of berkelium could not then provide the element, as they had temporarily ceased production. Plans to synthesize element 117 were suspended in favor of the synthesis of element 118, which was produced by bombarding a californium target with calcium. The Russian team sought to use berkelium because calcium-48, the isotope of calcium used in the beam, has 20 protons and 28 neutrons, making a neutron-proton ratio of 1.4. And it is the lightest stable or near-stable nucleus with such a large neutron excess. The second lightest such nucleus, palladium-110, is much heavier. Thanks to the neutron excess, the resulting nuclei were expected to be heavier and closer to the sought-after island of stability. Since ununseptium has 117 protons in its nucleus and calcium has 20, they needed to use berkelium, which has 97 protons in its nucleus. Discovery In 2008, the American team resumed production of berkelium, producing 22 milligrams of the element, enough to perform the experiment. The berkelium was subsequently cooled for 90 days and then chemically purified for another 90 days. The only isotope of berkelium that can be produced in weighable quantities is berkelium-249. Its half-life is only 330 days. After that time, half the berkelium produced would have decayed away. Because of this, the berkelium target had to be quickly transported to Russia. For the experiment to be viable, it had to begin within 6 months of its departure from the United States. In mid-2009, The target was packed into 5 lead containers to be sent on a commercial flight from New York to Moscow. Russian customs officials twice refused to let the target enter the country because of missing or incomplete paperwork. Over the span of a few days, the target traveled over the Atlantic Ocean 5 times. On its arrival in Russia, the berkelium was transferred to Dimitrov, Ulyanovsk Oblast, where it was deposited as a 300 nanometer thin layer on a titanium film. It was then transported to Dubna, where it was installed in the particle accelerator at JINR. The calcium-48 beam was generated by the Russian team by chemically extracting the small quantities of calcium-48 present in naturally occurring calcium. The experiment began in June 2009. In January 2010, scientists at the Flerov Laboratory of Nuclear Reactions announced internally that they had detected the decay of a new element with atomic number 117 via 2 decay chains, one of an odd-odd isotope undergoing 6 alpha decays before spontaneous fission, and one of an odd-even isotope undergoing 3 alpha decays before fission. On April 9, 2010, an official report was released in the journal Physical Review Letters identifying the isotopes as 294 UUS and 293 UUS, which were shown to have half-lives on the order of tens or hundreds of microseconds. The isotopes were formed as follows: 249, 97 Bk plus 48, 20 Ca 297, 117 UUS a 294, 117 UUS plus 31, 0 N, 249, 97 Bk plus 48, 20 Ca 297, 117 UUS a 293, 117 UUS plus 41, 0 N. Recognition equals. All of unseptium's daughter isotopes were previously unknown. Therefore, their properties could not be used to confirm the claim of discovery. In 2011, when one of the decay products was synthesized directly, its properties matched those measured in the claimed indirect synthesis from the decay of unseptium. The discoverers did not submit a claim for their findings in 2007–2011 when the Joint Working Party was reviewing claims of discoveries of new elements. The Dubna team repeated the experiment in 2012, creating 7 atoms of unseptium. The results of the experiment matched the previous outcome. The scientists have since filed an application to register the element. In 2014, a joint Germany-Euro-American collaboration of scientists from the ORNL and the GSI Helmholtz Center for Heavy Ion Research in Darmstadt, Germany, claimed to have confirmed discovery of the element. The team repeated the Dubna experiment using the Darmstadt accelerator, creating 2 atoms of unseptium 294. As of 2015, no official name has been suggested for unseptium. The discoverers will be given the right to suggest a name as soon as it is recognized by the JWP. A Dubna authority said in June 2012 that it could take up to a year before this happens. According to the guidelines of the International Union of Pure and Applied Chemistry, the names of new elements should end in -um. This includes unseptium, even if the element is a halogen, which traditionally have names ending in -ine. Using Mendeleev's nomenclature for unnamed and undiscovered elements, unseptium should be known as eka-astatine. Using the 1979 IUPAC recommendations, the element should be temporarily called unseptium until the discovery is confirmed and a permanent name chosen. Many scientists in the field call it element 117, with the symbol or 117. Predicted properties equals nuclear stability and isotopes equals. The stability of nuclei quickly decreases with the increase in atomic number after curium, element 96, whose half-life is 4 orders of magnitude longer than that of any subsequent element. All isotopes with an atomic number above 101 undergo radioactive decay with half-lives of less than 30 hours. No elements with atomic numbers above 82 have stable isotopes. Nevertheless, because of reasons not well understood yet, there is a slight increase of nuclear stability around atomic numbers 110–114, which leads to the appearance of what is known in nuclear physics as the island of stability. This concept, proposed by University of California professor Glenn Seaborg, explains why superheavy elements last longer than predicted. Unseptium is the second heaviest element created so far, and has a half-life of less than 1 second. This is longer than the predicted value used in the Discovery report. The Dubna team believes that the synthesis of the element is direct experimental proof of the existence of the island of stability. It has been calculated that the isotope 295U would have a half-life of 18 ± 7 milliseconds, and that it may be possible to produce this isotope via the same berkelium-calcium reaction used in the discoveries of the known isotopes, 293U and 294U. The chance of this reaction producing 295U is estimated to be, at most, 1/7 the chance of producing 294U. Calculations using the quantum tunneling model predict the existence of several isotopes of unseptium up to 303U. The most stable of these is expected to be 296U with an alpha decay half-life of 40 milliseconds. A liquid drop model study on the element's isotopes shows similar results. It suggests a general trend of increasing stability for isotopes heavier than 301U, with partial half-lives exceeding the age of the universe for the heaviest isotopes like 335U when beta decay is not considered. Atomic and physical equals, unseptium is expected to be a member of group 17 in the periodic table, below the 5 halogens. Fluorine, chlorine, bromine, iodine, and astatine, each of which has 7 valence electrons with a configuration of ns2np5. For unseptium, being in the 7th period of the periodic table, continuing the trend would predict a valence electron configuration of 7s27p5, and it would therefore be expected to behave similarly to the halogens in many respects that relate to this electronic state. Significant differences are likely to arise, largely due to spin-orbit interaction, the mutual interaction between the motion and spin of electrons. The spin-orbit interaction is especially strong for the superheavy elements because their electrons move faster at velocities comparable to the speed of light than those in lighter atoms. In unseptium atoms, this lowers the 7s and the 7p electron energy levels, stabilizing the corresponding electrons, although 2 of the 7p electron energy levels are more stabilized than the other 4. The stabilization of the 7s electrons is called the inert pair effect. The effect that separates the 7p subshell into the more stabilized and the less stabilized parts is called subshell splitting. Computational chemists understand the split as a change of the second quantum number L from 1 to 1/2 and 3/2 for the more stabilized and less stabilized parts of the 7p subshell, respectively. For many theoretical purposes, the valence electron configuration may be represented to reflect the 7p subshell split as 7s27p2, 1/27p3, 3/2. Differences for other electron levels also exist. For example, the 6d electron levels are both raised, so they are close in energy to the 7s ones, although no 6d electron chemistry has been predicted for unseptium. The difference between the 7p1/2 and 7p3/2 levels is abnormally high. 9.8 eV. Astatine's 6p subshell split is only 3.8 eV, and its 6p1/2 chemistry has already been called limited. These effects cause unseptium's chemistry to differ from those of its upper neighbors. Unseptium's first ionization in eka, the energy required to remove an electron from a neutral atom is predicted to be 7.7 eV, lower than those of the halogens, again following the trend. Like its neighbors in the periodic table, unseptium is expected to have the lowest electron affinity energy released when an electron is added to the atom in its group. 2.6 or 1.8 eV. The electron of the hypothetical hydrogen-like unseptium atom oxidized so it has only one electron, US116 plus is predicted to move so quickly that its mass is 1.9 times that of a non-moving electron, a feature attributable to relativistic effects. For comparison, the figure for hydrogen-like astatine is 1.27 and the figure for hydrogen-like iodine is 1.08. Simple extrapolations of relativity laws indicate a contraction of atomic radius. Advanced calculations show that the radius of an unseptium atom that has formed one covalent bond would be 165 pm, while that of astatine would be 147 pm. With the 7 outermost electrons removed, an unseptium is finally smaller. 57 pm for unseptium and 61 pm for astatine. The melting and boiling points of unseptium are not known. Earlier papers predicted about 350 500 degrees Celsius and 550 degrees Celsius respectively, or 350 550 degrees Celsius and 610 degrees Celsius respectively. These values exceed those of astatine and the lighter halogens, following periodic trends. A later paper predicts the boiling point of unseptium to be 345 degrees Celsius. The density of unseptium is expected to be between 7.1 and 7.3 Gauss-3, continuing the trend of increasing density among the halogens. That of astatine is estimated to be between 6.2 and 6.5 Gauss-3. Chemical. Unlike the previous group 17 elements, an unseptium may not exhibit chemical behavior common to the halogens. For example, extant members of the group routinely accept an electron to achieve the more stable electronic configuration of a noble gas, one having 8 electrons in its valence shell. This ability weakens as atomic weight increases going down the group. An unseptium would be the least willing to accept an electron. Of the oxidation states it is predicted to form, A1 is expected to be the least common. There is another opportunity for an unseptium to complete its octet by forming a covalent bond. Like the halogens, when two unseptium atoms meet they are expected to form a Z-US bond to give a diatomic molecule. Such molecules are commonly bound via single sigma bonds between the atoms. These are different from pi bonds, which are divided into two parts, each shifted in a direction perpendicular to the line between the atoms, and opposite one another rather than being located directly between the atoms they bind. Sigma bonding has been calculated to show a great anti-bonding character in the A2 molecule and is not as favorable energetically. An unseptium is predicted to continue the trend. A strong pi character should be seen in the bonding of US2. The molecule UUSCl is predicted to go further, being bonded with a single pi bond. Aside from the unstable A1 state, 3 more oxidation states are predicted. +5, +3, and +1. The +1 state should be especially stable because of the destabilization of the 3 outermost 7p3/2 electrons, forming a stable, half-filled subshell configuration. Astatine shows similar effects. The +3 state should be important, again due to the destabilized 7p3/2 electrons. The +5 state is predicted to be uncommon because the 7p1/2 electrons are oppositely stabilized. The +7 state has not been shown even computationally to be achievable. Because the 7's electrons are greatly stabilized, it has been hypothesized that an unseptium effectively has only 5 valence electrons. The simplest possible unseptium compound would be the monhydride, UUSH. The bonding is expected to be provided by a 7p3/2 electron of unseptium and the 1's electron of hydrogen. The non-bonding nature of the 7p1/2 spinner is because unseptium is expected not to form purely sigma or pi bonds. Therefore, the destabilized 7p3/2 spinner is responsible for bonding. This effect lengthens the UUSH molecule by 17 picometers compared with the overall length of 195 pm. Since the unseptium p-electron bonds are 2/3 sigma, the bond is only 2/3 as strong as it would be if unseptium featured no spin-orbit interactions. The molecule thus follows the trend for halogen hydrides, showing an increase in bond length and a decrease in dissociation energy compared to H. The molecules TLUS and UUTUUS may be viewed analogously, taking into account an opposite effect shown by the fact that the elements p1/2 electrons are stabilized. These two characteristics result in a relatively small dipole moment for TLUS. only 1.67 d, the positive value implying that the negative charge is on the unseptium atom. For UUTUUS, the strength of the effects are predicted to cause a transfer of the electron from the unseptium atom to the ununseptium atom, with the dipole moment value being a 1.80 d. The spin-orbit interaction increases the dissociation energy of the UUSF molecule because it lowers the electronegativity of unseptium, causing the bond with the extremely electronegative fluorine atom to have a more ionic character. Unseptium monofluoride should feature the strongest bonding of all group 17 element monofluorides. VSEPR theory predicts a bent T-shaped molecular geometry for the group 17 trifluorides. All known halogen trifluorides have this molecular geometry and have a structure of AX3E2, a central atom, denoted A, surrounded by 3 ligands, X, and 2 unshared electron pairs, E. If relativistic effects are ignored, UUSF3 should follow its lighter congeners in having a bent T-shaped molecular geometry. More sophisticated predictions show that this molecular geometry would not be energetically favored for UUSF3, predicting instead a trigonal planar molecular geometry. This shows that VSEPR theory may not be consistent for the superheavy elements. The UUSF3 molecule is predicted to be significantly stabilized by spin-orbit interactions. A possible rationale may be the large difference in electronegativity between unseptium and fluorine, giving the bond a partially ionic character. Notes. References. Bibliography.